Let's continue and let's find the number of diagonals for a pentagon. So we know the number of diagonals is the number of sides times the number of sides minus 3 over 2. And for a pentagon, the number of sides is 5. So the number of diagonals is going to be 5 times 5 minus 3 over 2. So the number of diagonals is going to be 5 times 2. 5 minus 3 is 2 over 2. All right, so what is 10 over 2? The number of diagonals for a pentagon is 5. How about if we're told how many diagonals we have and now they want to know how many sides it has? What type of polygon has 9 diagonals? Well, if the number of diagonals is going to equal the number of sides times the number of sides minus 3 over 2, and we are told there are 9 diagonals, I'm going to plug the 9 in for D. The number of diagonals is 9, and then I want to solve for n. All right, so I'm going to multiply both sides of the equation by 2 to get rid of that fraction. So 18 is going to equal n times n minus 3. So how am I going to solve for n? This is going to become a quadratic set equal to 0. So I'm going to distribute my n. 18 is going to be n squared minus 3n. And the only way to solve these is to set your quadratic equal to 0. N squared minus 3n minus 18. So what are two numbers multiplied together that equal negative 18, but when added together equal negative 3? A little bit of algebra here. Negative 6 and positive 3. If we were to multiply this first, outside, inside, last, we'd get our polynomial. Well, if that times that equals 0, that means n minus 6 equals 0, or n plus 3 equals 0. Here I'm going to add 6 to both sides. That would be a 6-sided object. Here I'm going to subtract 3 from both sides. And does it make sense to have a negative 3 number of sides? No, it does not. So we're going to disregard that answer. And the name of a polygon that has 6 sides is called a hexagon. So that is actually a hexagon that has 9 diagonals. All right, another characteristic of polygons is that we can know what the sum, when we add up all of the interior of the angles, should be. So we know for a triangle the sum of all the angles will always equal 180. Maybe you would know from a square, even though we haven't studied squares yet, the sum of all the interior angles of a quadrilateral is going to equal 360. Similarly, we can know the sum of the measure of all the interior angles by this equation right here. The sum is the number of sides minus 2 times 180 degrees. So in this example, they want us to find the sum of the measure of the interior angles of a hexagon, and then find the measure of each interior angle if it's equiangular. All right, so the sum is going to be the number of sides minus 2 times 180. And for a hexagon, n is equal to 6. All right, so the sum of all our angles is going to be 4 times 180. And 4 times 180 is 720 degrees. The sum of all the angles of a hexagon will add up to 720. Now, if this is an equiangular hexagon, all 6 have the same measure. So that means each individual angle, each interior angle, if they add up to 720, we're going to divide by 6. That means each interior angle would be 120 degrees. So we're kind of introducing you to this concept that polygons may have all the angles, may be equiangular. All the angles, all the interior angles may have the same measure. You know what? Here's an example of a hexagon that is equiangular. Do you see the little arcs saying all of these angles have the same measure? But you know what? The sides are not the same length. Here's a quadrilateral. The angles are not the same measure, but the sides are the same measure. Equilateral, equiangular. And here we have if all the angle measures are the same, congruent, and all the side measures, lengths are the same, congruent. If both conditions are true, this is called a regular polygon. So this would be a regular pentagon. All the sides have the same measure as each other, and all the angles, interior angles, have the same measure as each other. So a regular polygon is both equilateral and equiangular. And what that means is the measure of each interior angle. Here's my sum. The number of sides minus 2 over 180. That's the sum of all of the angles. If I divide that by the number of sides, that will be the measure of each angle. So we do have an example here. They want us to find the measure of each interior angle for this floor tile. It's equiangular and it is an octagon. It is an 8-sided object. Well, each angle will be the number of sides minus 2 times 180 divided by the number of sides. So each angle is going to be 6 times 180 divided by 8. So each angle is going to be 1080 divided by 8, which means each angle is 135 degrees for our example, our equiangular octagon. And some other things that we know about regular polygons: the sum of the measure of 4 angles of a quadrilateral will always be 360. We saw that with our square. And the sum of the measure of the exterior angles of any polygon will always equal 360. This would be for any polygon if you add up the measures of all the exterior angles. And if it is a regular polygon, the measure of an exterior angle will always be 360 divided by the number of sides. So if it's a 10-sided polygon, if it's a decagon, each exterior angle is going to be 360 divided by 10. Each exterior angle is going to be 36 degrees. And when you add up all 10 of them, that would equal 360. And one last kind of interesting note is not just polygons, but there is another figure called a polygram. And that's a star-shaped object that gets created when you extend the sides. when you extend the sides of any convex polygon. And the name of the polygon will come from the name of the polygon that's being extended. So as an example, here's a hexagon. That's a six-sided object. 1, 2, 3, 4, 5, 6. This is a hexagon, a six-sided object. If I extend each of the sides, and you have to make sure you get all 6 sides. Here I missed one. Extend this side and extend, and extend this side. The intersection points will be the points of your hexagram, So it was called a hexagon. The interior object is called a hexagon. So the star-shaped object is a hexagram. I'll just kind of get rid of those so that you can see just the hexagram there. So extend the sides of a polygon and you'll get a polygram. There you go.